Okay. Hey everyone, I'm Julian, and as the title of the presentation says, I wanted to talk to you about how explanations are not really suitable to help people spot discrimination, okay? Algorithmic discrimination. So, does it work? No, it doesn't work. Okay. Okay, so let's start with the beginning. I know you all know what algorithmic discrimination is, because this is a fairness conference, but so that we have the same understanding. So we can invert that question and ask what is non-discrimination, fairness, and this is an equitable treatment of different protected groups by machine learning models. And what this means is that the predictions of these models and their performance does not change across these protected groups, okay? So we can think about an example in which you have a model that predicts whether someone should get approved for a loan or not based on their income and credit history. And a test for discrimination you can have is ask whether a rejected female applicant would actually get approved if she somehow managed to apply as a man. All right, but this is just the intuition. It's not really clear what it means to somehow apply with a different protected attribute, because like the machine learning models, they don't see the protected class. They usually see just a bunch of features, among which there are features that are proxies, that are causally dependent on the protected class. So what we do here is we use the formalization of counterfactual fairness, or our relaxation of it, delta counterfactual fairness. I know this is math heavy, but just bear with me, I'm going to walk you through it. So what counterfactual fairness does, it looks at the distance between two probabilities, the probability that we obtain the prediction as it is with the current value of the protected attribute, and the probability that we obtain the same prediction, but once we intervene on the protected attribute and change it, and then propagate that change onto other features that are causally dependent on the protected attribute. So in our example, we would propagate the change on the credit history. And then we would see how the probability of obtaining the same prediction change as we do that. Okay, so we compare these two probabilities and we want them to be close to each other at most delta. So if you apply you can trust me on it, the laws of probability on it, you're going to get that this is really the expression at the bottom, which is the probability that the prediction flips if we intervene on the protected attribute. So if that probability is too high, then we say we have to deal with discrimination, otherwise it's fair. Okay, so with this, we can actually define what sort of task people are supposed to be solving when they're seeing explanations. So what they would need to do when seeing the explanations is to somehow retrieve the ground truth discrimination label on each prediction. Because if we have the causal model, we have the probabilities, we can set this ground truth discrimination label by checking whether the flip rate, the probability that prediction flips if we intervene on the protected attribute, is larger than delta or not. And what people are doing, they're trying to give their own labels to these predictions, trying to find discrimination. And this really casts the problem as a classification task, or even a better detection task. And this is good because we can use standard classification metrics and measures in order to measure how well people are doing in detecting discrimination. So there are a lot of reasons why explanations could fail and people could not use them to spot discrimination. First of all, explanations. There are many explanations for every prediction, multiplicity, and it's possible that the explanation a person is seeing is hiding information about the proxies and discrimination. Second of all, people might just not know how to use explanations. Like if you deal with feature attribution methods, which list how important features are, it's not really clear how to use them to support claims about discrimination. Then people might know the causality and all that stuff, but they might misrepresent how strong the proxy is. They might believe, for instance, that the credit history is a very strong proxy, when in reality it's a weak proxy. They might not also know the protected class of a point. If you think about a third-party audit in which the protected class is hidden, people might not know how to simulate the flip rate and the probability the prediction changes when we intervene on the protected attribute. And finally, they might have just wrong causal beliefs. They might think that some feature is a proxy when in reality it's not, and vice versa. So what we do here in this paper, in this study, is that we create a study, a synthetic experiment, in which we control for these confounds in order to evaluate how well explanations are doing in isolation, how good they are. And in our study, there's a NASA model. NASA is sending robots to Mars, and it uses the model to predict which robots will break down, which are defective or which are reliable. And it needs to be fair with respect to the company that produces the robots when it's purchasing the robots. There are two companies, Company X and Company S, they're producing the robots. The robots differ in body parts. There are 4 binary body parts. There are only 4 distinct robots, but they differ between companies. And the model can discriminate against one of the companies because it says that robots with antennas are more reliable. And it just happens to be that one of the companies produces more robots with antennas. Okay? So what we do is we explain all that to people. We explain to them how to spot discrimination. And in this case, we show them counterfactual explanations. There are explanations which show you which input features would need to be changed in order to flip the prediction. And we tell them about discrimination. We teach them how to use explanations. We test all that in our setup so people have sort of the knowledge that we would expect auditors to have. We also show them an anchoring set of robots to anchor their beliefs to a certain strength of the proxy. And then we elicit what sort of things they learn about this when we ask them which protected class they think each robot has, and what is the relationship between the outcome variable and which is the reliability in the proxy. How does adding or removing the antenna change things? And then they go through multiple rounds of predicting whether a prediction is discriminatory or not based on the explanation that shows you which parts needs to be changed in the robot. So we ran this in multiple versions, regimes in which we vary the strength of the proxy and we vary how much insight people have into the problem, if they know the protected attribute, if they know the strength of the proxy. And if you wonder how they did very, very badly. So in the vanilla case, when they know just what we told them, their detection performance, this is the number of correct detections among all detections they made, is around 50%. And they miss a lot of the discriminatory cases, around 50% as well, and they have a constant false positive rate of about 30%. If we additionally assume that they know more, and they know, for instance, the protected class, then this does not change the results significantly. The detection is around 55%. If we really just change the whole setup of the world and the causal model to adapt it to their beliefs, then this significantly improves the results, but still the detection is around 60-65%, but for a very special case of a strong proxy in which every prediction that depends on the proxy is discriminatory, and people are just very brazen at just saying that whenever they see a proxy in the explanation, it must be discrimination. So this is correct in that case, but this is a very special case. We also checked, okay, maybe they didn't see all of the explanations, so we showed them additional explanations so that they knew for sure whether a prediction can be flipped with a proxy or not. But and they knew how to use multiple explanations, but this just confused them more and their detection dropped around 40%. And why is it all important? Well, it's important because regulations around the world are currently introducing right to an explanation partially as a safeguard against discrimination. And this is just not working. We're introducing laws that are ineffective. And therefore, if we care about fairness, we need to create new laws and create new techniques. Thank you very much.